At first glance, a bifurcation might sound like a technical detail buried deep in a math textbook, some obscure point where a system changes its behavior. But look closer and you'll find bifurcations everywhere in how a river splits, how your heart beats, how a bridge begins to wobble before collapse, or even how entire ecosystems suddenly flip into a new state. In science, a bifurcation refers to a critical point where a system undergoes a qualitative change in behavior, often triggered by a small, gradual shift in parameters. And it is precisely this ability to trigger big change from subtle causes that makes bifurcations not just interesting, but profoundly useful. Let's take a step back. In mathematics and physics, bifurcations are studied within dynamical systems theory, systems that evolve over time according to specific rules. Imagine a ball resting at the bottom of a valley. As long as you gently push it, it stays in place or rolls back. But raise the slope just slightly, and suddenly the ball tips over into a new valley. It changes state. That's a bifurcation, a small parameter change, causing a sudden, irreversible shift in system behavior, the ball's position. There are many types of bifurcations: saddle node, Hopf, pitchfork, period doubling, and more. Each one describes a different kind of transition, from steady state to oscillation, from order to chaos, from stability to collapse. But no matter the form, they all mark tipping points, places where prediction breaks down and new behavior emerges. One famous example is in population dynamics. Consider a species living in an ecosystem. If the birth rate exceeds the death rate, the population grows. But if conditions gradually worsen, say food becomes scarce, the population may remain stable for a while, then suddenly crash to extinction. That crash is a bifurcation, a nonlinear leap from one equilibrium, healthy population, triggered by a continuous change in just one parameter, resources. But bifurcations aren't just theoretical, they're incredibly practical. In engineering, understanding bifurcations is critical to preventing disasters. For instance, when wind hits a suspension bridge at just the right speed, it can cause a Hopf bifurcation, shifting the bridge from stable stillness to violent oscillation. The infamous collapse of the Tacoma Narrows Bridge in 1940 was a dramatic, real-world example of this. Engineers now model these transitions carefully to design safer buildings, aircraft, and vehicles. In medicine, bifurcations help explain phenomena like heart arrhythmias or epileptic seizures. Your heart normally beats in a regular rhythm, but small shifts in electrical or chemical parameters can push it past a bifurcation point, triggering chaotic or unstable rhythms. The same goes for neural circuits. Understanding how bifurcations work in the brain could improve early detection of seizures, mental health disorders, or even consciousness states under anesthesia. In climate science, bifurcations are used to model tipping points, such as ice sheet collapse, Amazon rainforest dieback, or the disruption of ocean currents. These are systems that may look stable until a slow, invisible change reaches a point of no return. Bifurcation theory gives researchers tools to identify early warning signals, helping predict catastrophic shifts before they occur. Even in economics and social science, bifurcations play a role. Stock markets can crash, political systems can destabilize, and public opinion can flip, all from small shifts amplified by nonlinear feedback. Models that include bifurcations help economists and analysts understand how systems transition from growth to recession or from cooperation to conflict. You might ask, can bifurcations be controlled or harnessed? Absolutely. In control theory, bifurcation management is an entire subfield. By tweaking inputs, applying feedback, or changing constraints, scientists can prevent unwanted bifurcations like collapse or chaos, or even induce them intentionally, like in mode slipsing devices or reconfigurable robots. And in synthetic biology, bifurcations are used to design genetic switches, biological systems that flip between states in response to external cues. Want a cell to start producing insulin only when glucose crosses a threshold? That's a bifurcation waiting to happen, engineered with precise genetic circuits. So, what's the deeper meaning of bifurcations? They remind us that not all change is gradual. Sometimes a system resists change for a long time, then flips, suddenly and irreversibly. Understanding bifurcations allows us to predict, model, and even steer these critical transitions across physics, biology, ecology, technology, and society. And perhaps that's the most profound lesson. Bifurcations reveal the fragile edge between stability and transformation. They show that the world is not just built on gradual shifts, but on thresholds, and that by identifying and respecting those thresholds, we can navigate complexity, prevent collapse, and engineer breakthroughs. In short, bifurcations are the science of sudden change. And knowing how to read their signs might just help us stay one step ahead of chaos. Bifurcation refers to the phenomenon where a small, continuous change in a system's parameter leads to a sudden qualitative change in its long-term behavior. This occurs in nonlinear dynamical systems when their equilibrium or periodic states lose stability and new solutions emerge. Bifurcation theory captures the critical points at which systems transition between fundamentally different modes of operation, revealing how complexity and instability arise in otherwise stable systems. In a population model governed by the logistic equation, a small increase in the reproduction rate can cause the population to shift from a stable state to periodic cycles or even chaotic oscillations. It's like slowly turning the volume knob on a radio and suddenly jumping from silence to unexpected static. Crossing an invisible threshold transforms the whole experience. Structural shifts in bifurcating systems refer to the emergence or disappearance of fixed points or periodic orbits as parameters are varied. These shifts are not random but are governed by intrinsic mathematical laws that dictate how the system's geometry and stability evolve. Unlike linear systems, which respond proportionally to inputs, nonlinear systems can dramatically reorganize themselves near bifurcation points, leading to unpredictability or new behavior patterns. As the speed of a spinning top decreases, it transitions from steady spinning to a wobbling motion before eventually toppling. This change marks a bifurcation in its dynamic stability. It's like a train track suddenly splitting into two routes. Depending on subtle shifts in the switch, the train ends up on a completely different path. Bifurcations occur when local dynamics in a system interact with changing parameters, such as feedback strength or environmental influence. These interactions alter the stability of equilibria, allowing the system to explore new states. Key mechanisms include pitchfork, saddle node, and Hopf bifurcations, each describing a different way in which stability is lost and new behaviors emerge. These changes are crucial for understanding how complex behavior arises even in systems governed by simple equations. In climate models, small increases in greenhouse gases can trigger abrupt shifts in ocean circulation patterns, marking bifurcations in Earth's climate system. It's like a balance scale where adding just one more grain of sand causes the entire structure to tip. A minor input results in a major change. Bifurcations are central to complexity science because they explain how systems evolve from order to disorder, or vice versa. They illustrate that complex patterns or chaotic behavior can originate from deterministic systems as parameters cross specific thresholds. These transitions often underpin critical phenomena such as the onset of turbulence, neuronal firing, or market crashes, demonstrating how systemic shifts can emerge from continuous changes in inputs. In neural systems, the sudden firing of a neuron occurs when membrane voltage crosses a threshold, representing a bifurcation from a resting to an active state. It's like a crowd suddenly erupting in applause after a moment of silence, not due to one loud clap, but because a tipping point was quietly passed. Bifurcations often occur in open-driven systems where energy input maintains the system far from equilibrium. These energy flows allow systems to traverse through bifurcation points and settle into new attractors. Thermodynamically, such transitions illustrate how systems can locally reduce entropy by forming structure while still obeying global entropy increase. Thus, bifurcations connect nonlinear dynamics with the broader principles of non-equilibrium thermodynamics. In Rayleigh-Benard convection, heating a fluid layer from below can cause the system to bifurcate from uniform conduction to an organized array of convection cells. It's like turning on a stove under still water. The moment the heat is sufficient, spontaneous patterns form, driven entirely by the energy input. Bifurcations are closely linked with changes in informational complexity. As systems cross critical points, their behavior transitions from predictable to unpredictable, increasing their entropy or mutual information content. Information theoretic measures like transfer entropy or statistical complexity can quantify the richness of behavior emerging at and beyond bifurcations. These tools help identify early warning signals of approaching criticality in both natural and artificial systems. In financial systems, a sudden increase in volatility can be traced to a bifurcation in investor behavior, where market sentiment shifts from stable expectations to rapid speculation. It's like seeing storm clouds gathering on the horizon. You can sense that something big is about to change, even if the precise details remain uncertain. Bifurcations are foundational in modeling biological transitions, from heartbeat dynamics and gene expression to ecological population collapses. In artificial systems like robots and neural networks, bifurcation principles are used to design adaptive responses and optimize learning dynamics. The ability of systems to switch behavior modes through internal dynamics rather than external control makes bifurcations valuable in designing resilience and adaptability. In synthetic biology, bifurcation analysis helps design genetic circuits that switch between distinct expression states, acting as biological memory units. It's like a smart thermostat that autonomously flips between heating and cooling, not because of explicit commands, but because it internally detects the need for change. Despite their explanatory power, bifurcations are challenging to predict in real systems due to noise, high dimensionality, and sensitivity to initial conditions. Slight errors in parameter estimation can lead to large discrepancies in outcomes. Moreover, in multistable systems, predicting which attractor the system will settle into post-bifurcation is inherently difficult. Control strategies such as feedback loops or parameter tuning aim to delay or exploit bifurcations for desired outcomes. In cardiac defibrillation, controlling the bifurcation that leads to ventricular fibrillation is critical to preventing sudden cardiac death. It's like walking a tightrope. The slightest misstep can lead you down an entirely different path, one that is difficult to reverse once taken. Future research on bifurcations will integrate machine learning, experimental data, and high-performance computing to enhance prediction and control. This has implications across disciplines, from designing resilient cities and smart grids to building adaptive algorithms and understanding brain dynamics. A deeper understanding of bifurcations may unlock the principles behind critical decision-making, adaptive behavior, and systemic transformation. Interdisciplinary efforts are using bifurcation theory to predict tipping points in ecosystems and global climate models, aiding policy decisions for sustainability. It's like discovering the pressure points of a massive machine. Know where and when to apply force, and you can steer the system toward balance or change